Welcome back to the deep dive. Today we're jumping into some really fascinating work presented at SIGGRAPH 25. It's a paper from NYU, AMD, and Intel called ImageGS, Content Adaptive Image Representation via 2D Gaussians.
Right, ImageGS. It's quite an interesting take.
It really is, and it tackles a problem that's just getting bigger, isn't it? This explosion of high-res visual content, from games, AI art, all that stuff. How do we handle it efficiently?
Yeah.
Especially on devices that aren't super powerful.
Exactly. Resource constraints are a major bottleneck.
And the paper's approach is, well, kind of surprising. Using 2D Gaussians, inspired by the 3D radiance fieldwork.
It leverages that success, but adapts it cleverly for images.
Okay, let's unpack this. We're diving into some truly groundbreaking work that could fundamentally redefine how we approach image compression, rendering, maybe even how we think about visual data itself. It's these 2D Gaussians, these sort of simple geometric shapes doing the heavy lifting.
Indeed. And what's fascinating here, I think, is how ImageGS tries to get past the limitations of, well, both traditional methods and even some of the newer neural approaches.
Limitations for real-time stuff, you mean?
Precisely. Real-time applications. Think gaming, AR, VR. Many current methods just stumble there. Either they use fixed data structures, which aren't really adaptive to the image content itself.
Right, like a uniform grid for a non-uniform image?
Exactly. Or they use these computationally heavy implicit neural models. Powerful, yes, but often too slow for dynamic interactive use. Scalability is a real issue.
Okay.
So ImageGS comes in with this genuinely content-adaptive representation. It models the image as a collection of these anisotropic colored 2D Gaussians.
Anisotropic meaning they can stretch and orient, right? Not just circles.
Correct. They can better conform to image structures like edges or textures. And the whole design is really geared towards hitting that sweet spot. Great visual quality for a very small data size. That's the rate distortion trade-off, plus hardware-friendly random access, which is critical.
For GPUs and real-time rendering.
Yes, and flexible quality control. It's built on explicit features, position, shape, color things with, physical meaning, which is a bit different from the pure black box feel of some implicit models.
Makes sense.
So the key benefits really boil down to superior visual fidelity, much better memory efficiency, and really fast decoding. It seems especially good for stylized images, textures, and these low bitrate situations where every bit just has to count.
That's a great setup, and it really underscores the need for something like this. Let's dig into that motivation a bit more, because the problem itself is quite significant. We've just seen this, explosion of high-res content, right?
Oh, absolutely.
Generative AI is churning out incredible assets for games, VR, design. It's everywhere. People are documenting this like crazy. But the challenge is getting that rich content onto actual devices. Your phone, maybe an AR headset, or just streaming it smoothly online.
Right, the deployment bottleneck.
Yeah. And the old standbys. PNG, JPEG. They're showing their age in this context. JPEG can look blocky or fuzzy at low bitrates, and decoding isn't free. PNG is lossless, great, but the files are often huge.
Impractical for streaming or constrained storage? Definitely.
There was that paper by Vaidyanathan and others in 23 highlighting this exact trade-off, compression efficiency versus decoding speed. We need something more agile now. It's not just about storing images anymore.
Precisely. And, the field has responded. Neural image representations definitely emerged as a very promising path. We saw work from Chen, Tansik, others, showing how networks could encode images really efficiently, often better visually than traditional codec.
Right, the potential was clear.
And here's the but for real-time graphics.
Yeah.
Even these neural methods have their own hurdles.
All right.
A lot of them, for instance, rely on fixed data structures. Think multi-resolution hash grids, feature planes, things like that. We saw them in papers by Chen again, Carnivore.
Right, like instant MGP uses hash grids.
Exactly. And while they can be fast, that fixed structure means they lack true content adaptivity. They might spend just as much memory on a smooth, empty patch of sky as on a really intricate, detailed area. It's not optimal resource use.
I see. Inefficient.
Then you have the other camp. The compute-heavy implicit models, Sirens, other coordinate networks, Sergidam, Sitzman explore these. They can achieve incredible fidelity, representing the image as this continuous function.
But they're slow to query.
Very. Getting a single pixel color often means a full network pass. So decoding is slow. Scalability is poor for real-time frame rates. Just not practical for interactive graphics where you need speed above all else.
Okay, so that's the gap ImageGS is aiming for.
Yeah. If we connect this to the bigger picture, the challenge isn't just compression anymore. It's about achieving that compression while enabling real-time utility in dynamic settings.
Yeah.
Fast random access, dynamic quality adaptation. Ackman, Muller, and others pointed this out years ago. That's where many neural methods haven't quite delivered yet.
Right. That makes perfect sense. So the core idea in ImageGS to bridge this gap, here's where it gets really interesting, is to ditch the pixels, ditch the complex implicit networks, and use these 2D Gaussians instead, representing the image as just a collection of them.
Yeah, these fundamental geometric primitives.
And each Gaussian isn't just a blob, it's precisely defined, right? It has parameters.
Correct. Trainable parameters.
First, there's its position, the mean vector, a Schuer one, that's just its 2D coordinates at center point.
Yep, X and Y.
Then the shape and orientation, that's the covariance matrix, sigma nuller, a 2x2 matrix telling it how stretched or rotated it is. That's the key to the anisotropic part, letting it fit lines and edges.
Exactly. It dictates the shape.
And finally, each one has a color vector, $7. And you mentioned this is flexible. The dimension nullers can vary.
Yes, that's quite neat. So it can handle grayscale, N1, RGB, N3, or even these multi-channel texture formats used in games where you might pack, say, color, normals, roughness all together, and could be 9 or more.
Very versatile. Okay, and there was a detail about making sure this covariance matrix behaves during training.
Ah, yes, the stability aspect. That's crucial. The covariance matrix sigma needs to stay positive, semi-definite. Mathematically, that means it represents a valid convex shape and doesn't, collapse or invert during optimization.
Which could easily happen with numerical methods.
It could. So instead of optimizing the 4 elements of sigma directly, they use a factorized form. They break it down using a rotation matrix, 20s, and a scaling matrix, Stalers. So it looks like STRT.
Okay.
What this means practically is they optimize simpler components. Just a single rotation angle, tetral controlling the orientation, and a 2D scaling vector as a layer, control the extent along its main axis. Optimizing these ensures the resulting sigma is always well-behaved. It's a smart bit of engineering for robustness.
Makes the whole learning process much more stable, I imagine.
Definitely. It avoids a lot of potential numerical pitfalls.
So you mentioned the inspiration from 3D Gaussian splatting, the Kerbal paper, but you also said ImageGS is quite different in key ways for the 2D case.
Yes, absolutely vital distinctions. In 3D, they need view-dependent appearance, usually modeled with spherical harmonics, because the color of a 3D object can change based on where you view it from.
Right. Makes sense for 3D scenes.
But for a 2D image, that's a fixed view. No need for that complexity. So ImageGS skips the spherical harmonics entirely.
Simpler.
Much simpler. Also, 3D splatting needs an opacity attribute for each Gaussian and critically depth sorting during rendering. You have to figure out which Gaussians are in front of others to blend them correctly. That's computationally quite involved.
And for a flat 2D image.
No need for opacity or depth sorting. The color contributions of overlapping 2D Gaussians just add up at each pixel. The order doesn't matter. This massively simplifies the rendering pipeline.
Wow, okay. So each 2D Gaussian is pretty lightweight then.
Extremely lightweight, just $5 plus 9 parameters total. 2 for the mean position, 1 for the rotation theta, 2 for the scaling Cs, and more dollars for the color Cs.
That's it. So this raises an important question. How do these simplified 2D Gaussians still achieve such high fidelity? If they're so simple, how do they capture complex images so well?
That's the million-dollar question, isn't it? And the answer lies in, well, some very clever design choices in both the rendering mechanism and the optimization strategy. They really exploit the properties of 2D image synthesis effectively.
Okay, so let's get into that rendering mechanism. We have potentially thousands of these lightweight Gaussians. How do they actually get combined to make the final image? You mentioned a naive approach first.
Right. The authors mention it as a starting point conceptually. Equation 4 in the paper. You could theoretically calculate the color for a pixel math BFX by just summing up the contributions of every single Gaussian and all of them. So to say I have hex the math BFX, where d war of x is how much the ith Gaussian contributes at that pixel location.
Simple idea, but sounds slow.
Extremely slow. Imagine a 2K image, tens of thousands of Gaussians, doing that sum for every pixel. Astronomically expensive, it kills rendering speed, kills training speed.
You mentioned data locality issues too.
Yes, that's almost as critical for GPUs. If each pixel needs data from all Gaussians scattered across memory, you get terrible cache performance, constant memory stalls. GPUs need data neatly arranged to work fast. This naive approach is the opposite of that. It just wouldn't scale for real time.
So completely impractical. What's the optimized solution then?
The solution is this really smart tile-based rendering approach. It takes inspiration from other highly parallel graphics work like Lasner and Zollhofer stuff. This is the key to making image.js fast and GP feeling.
Tile-based, so they break the image up.
Exactly. Step 1, divide the image into a grid of small, non-overlapping tiles, say 16 by 16 pixels each. This immediately allows for parallel processing. Each tile can be handled independently by the GPU.
Okay, makes sense.
Step 2, a bit of pre-computation. For every Gaussian, figure out its rough spatial extent, specifically its 3 sigma range, which captures almost all its visual contribution. Then, find a bounding circle around that.
A bounding circle? Why?
To quickly figure out which Gaussians could possibly affect which tiles, it lets you build lists for each tile of only the potentially relevant Gaussians nearby. You don't need to consider faraway Gaussians at all. Prunes the problem massively.
Well, clever culling. Got it.
Step 3. Render pixels within a tile. Now, for a pixel math BFS in a tile, you only consider the Gaussians associated with that tile. And even then, you don't use all of them. You calculate their contribution and rank them.
Rank them?
Yeah, based on how much they contribute to that specific pixel. And here's the crucial bit. You only keep the top K contributors. K is usually small, like 10.
So for each pixel, you only blend the, say, 10 strongest Gaussians affecting it.
Precisely. Step 4. Take those top K Gaussians, normalize their contributions, they sum nicely, and then aggregate their weighted colors. That gives you the final pixel color CRI math BFX, as shown in equation 5.
Okay, that sounds much more manageable computationally.
Massively more. It solves the speed issue, promotes data locality, because each tile only accesses nearby Gaussian data, and that top K selection actually acts as a kind of helpful regularization during training too. Table 1 shows it improves quality.
Interesting. And they use CUDA for this.
Oh yes, custom CUDA kernels for the core parts of this tile-based rendering. Essential to squeeze out maximum parallelism and speed on the GPU. It's a very performance-engineered pipeline.
Right, the engineering really shines through there. Okay, so that covers how they get from Gaussians to an image efficiently. Let's switch gears to how they learn the right Gaussians in the first place. You mentioned earlier that using explicit features like Gaussians allows for smarter initialization compared to, say, neural networks starting from random weights.
Exactly. This is a significant advantage. Neural nets often need a lot of training data and time to learn meaningful representations from scratch. With explicit primitives like Gaussians, you can be much more direct and content-aware right from the beginning.
So what does this all mean for the actual learning process? It sounds like it's not just gradient descent on random parameters. There's more intelligence built in.
There absolutely is. They employ several content adaptive strategies, both for initialization and during the optimization itself.
Let's start with that initialization. How do they place the first batch of Gaussians?
It's not random. It's content adaptive position initialization. The probability, Kenneth, of placing a Gaussian at pixel math BFX is guided by the image content itself. Specifically, as equation 6 shows, it's a mix of two things.
Right.
One part is proportional to the local image gradient magnitude. High gradient means edges, textures, details. So more Gaussians get placed in these visually complex regions automatically. It focuses resources where they're needed most.
Smart. And the second part?
A simple uniform term. This just ensures some baseline coverage everywhere, even in smooth areas, so you don't get big empty patches. There's a weighting factor, lambda on it, typically set around 0.3, to balance between focusing on details and uniform coverage.
And what about the initial color?
Also content-aware. When a Gaussian is initialized at position math BFES, its initial color is simply set to the target image's color at that exact pixel, CAFE MEFST. So it starts with a very reasonable guess for its color.
Gives the optimizer a good head start.
A huge head start. Now, the optimization process itself, it's iterative. You render the current Gaussians using that tile-based method, equation 5. You compare the rendered image to the target image using a loss function specifically, a combination of L1 loss and S.
Why both L1 and SM?
L1 gives a good, robust pixel difference, while SM is better at capturing perceptual similarity, how humans see the quality. Combining them works well. And because the whole rendering pipeline is differentiable.
You can backpropagate the error.
Exactly. You compute gradients for all the Gaussian parameters, position BO, rotation zeta theta, scaling color valor, and update them using the optimizer, typically Atom, to minimize the loss.
And you mentioned a trick with the scaling.
Ah, yes, the inverse scale optimization. Instead of optimizing the scale values directly, which can range from very small to very large and make gradients unstable, they optimize $1
The inverse. Why?
It maps the scale values to a nicer range, often between 0 and 1, making the optimization landscape smoother. Think of it like adjusting a dial. Optimizing the inverse makes the dial less sensitive, easier to tune precisely. Their ablations show this really helps convergent speed and stability.
Clever. And it doesn't stop there. There's progressive optimization, too.
Right. Air-guided Gaussian addition. They don't just start with a fixed number of Gaussians and optimize them. The system dynamically adds more Gaussians during training, specifically targeting areas where the reconstruction error remains high.
So it focuses on the problem spots.
Precisely. There's another sampling probability, MEF-BS, described in equation 7, which is proportional to the current absolute reconstruction error at pixel math BFX. So new Gaussians preferentially pop up where the model is still struggling to match the target image.
And this helps refine details.
Exactly. It efficiently allocates new resources to fix local deficiencies. Figure 2 in the paper shows this whole pipeline visually, and Figure 13 is great. It shows how this progressive addition naturally creates a smooth level of detail LOD structure and leads to really good rate distortion curves.
That LOD aspect sounds very practical, and they tested all these components.
Rigorously. The ablation studies in Table 1 are key. They compare the full image GS model against versions where they switch off specific things. The content-aware position initialization, the color initialization, the inverse scale trick, the top K rendering normalization.
And the results.
Performance drops significantly in PSNR and MSSSM when you remove any of these components. It clearly validates that each piece, the smart initialization, the inverse scales, the top K rendering, plays a critical role in achieving both high quality and efficient convergence.
That's really thorough. It paints a picture of a system where every component has been carefully considered and empirically validated. Okay, so the design is clever, the optimization is smart. Now let's talk about the results. Does this innovative approach actually deliver time for the experimental validation?
Right, the proof is in the pudding, as they say.
Let's set the scene first. What kind of data did they test this on? It wasn't just standard image data sets, right?
No, and that's important. They curated a specific data set of 45 high-resolution 2K RGB images. Critically, these span 5 categories: vector art, photos, digital art, anime, and paintings. 9 images each, sourced from Adobe stock Polyhaven.
Why focus on those types?
Because, as they point out, maybe standard compression datasets like Kodak or CLIC are mostly lower-res natural photos. But today's graphics pipelines are full of high-res stylized content, AI-generated assets. There was a gap in evaluation benchmarks for that kind of content.
Makes sense. What else was in the test set?
For texture compression, they used 19 texture stacks, each with 9 channels. Again, 2K by 2K, representative complex game assets. And they did also include the standard CLIC 2020 dataset for comparison on natural images.
Got it. And the metrics, how did they measure success?
A whole suite of metrics for image quality. PSNR, MSSSim, LPIPS, which is learned perceptual similarity, and FLIP, another perceptual metric. For textures, PSNR and SSIM, and of course model size and KB and bitrate, PPP or PPPC, to measure compression efficiency.
Okay, comprehensive metrics. What about the implementation details?
Built on the gsplat library, which is open source for Gaussian splatting rendering, but they added their own custom CUD kernels for the key 2D rendering parts, like that tile-based top K approach.
To maximize speed.
Exactly. Everything orchestrated in PyTorch. They use float16 for the Gaussian parameters to save memory and speed things up. The initialization used those content-adaptive methods we discussed. Atom optimizer, specific learning rates for each parameter type.
Optimize inverse scales.
Yes, the loss was L1 plus 0.1 times SM loss. Trained for 5,000 steps. Key hyperparameters. K10 for the top K rendering, lambda at 0.3 for the initialization balance. And that progressive optimization started with half the Gaussians, adding more every 500 steps.
Very detailed setup. Okay, let's get to the juicy part. The findings. How did ImageGS perform?
Exceptionally well, particularly in its target areas. Let's look at visual fidelity versus memory efficiency first. Figures 3 and 13 really tell the story here. ImageGS hits remarkable quality levels at ultra-low bitrates.
Like how low?
For instance, at just 0.366 bits per pixel, which is very compressed for 2K images, they report 32.99 dB PSNR and 0.966 molas SM. That's high fidelity. Pushing it even further, down to 0.122 BPP, they still get 29.20 PSNR and 0.924 MSSSM, plus good LPFSF flip scores.
Wow, that's impressive resilience at low bitrates.
It really is.
Yeah.
And that progressive optimization, it naturally creates that smooth level of detail hierarchy they talked about. So you optimize once, and you get a representation that can be decoded in various quality levels on the fly. Super flexible for deployment.
Huge practical advantage. What about image compression performance compared to other methods?
Clear wins here, too, shown in figures 3, 7, 12. It consistently outperforms the neural baselines they tested. Real UF, Siren, FFN, Wire, INGP, GI across the bitrate range they looked at.
Better than all those neural approaches.
Yes, and perhaps more surprisingly, below about 0.244 BPP, it significantly beats JPEG. And that's without using entropy coding, which means it keeps its nice random access properties.
Beat JPEG without entropy coding, that's strong.
It is. Qualitatively, the comparisons show that at low bitrates, other methods often show artifacts like the blocking you get from grid-based methods like INGP when you shrink the grid. ImageGS tends to avoid those, giving a more natural degradation.
But you mentioned a caveat for natural images.
Right. On the CLIC 2020 Natural Image Dataset, Figure 5, the performance wasn't quite as dominant. Still decent, but not crushing the competition like on stylized content.
Why a difference?
They suggest it's partly the lower resolution, meaning fewer Gaussians overall, and partly that natural photos have a lot of fine-grained, pixel-level noise and detail that the explicit Gaussians, with a limited budget, struggle to capture perfectly. It prioritizes structure over noise, which is good sometimes, but can lose micro-detail.
Okay, an area for potential improvement. What about speed? System performance.
It's another major strength. Figure 4 shows it. Training is fast. 10,000 Gaussians on a 2K image, 1,000 steps, takes under 19 seconds on an A6000 GPU.
19 seconds. That's quick for optimizing a 2K representation.
Very quick. And rendering the crucial part for deployment is incredibly fast. 10,000 Gaussians render in just 0.00037 seconds.
Whoa, that's over 270 frames per second.
Easily, even 50,000 Gaussians render in under 5 milliseconds. And convergence during training is rapid too. Gets 95% of the final quality in under 400 steps, 99% within 2,000 steps. It learns efficiently.
Impressive speed stats. And finally, texture compression. Against things like BCN or ASTC.
Consistently better than BC1 and BC7, which are common industry standards. And it achieves performance comparable to ASTC, especially at very low bitrates. For instance, 32.20 dB PSNR at just 0.059 bits per pixel per channel for those 9-channel textures. That's really efficient for complex texture data.
So it's efficient, it's high quality, and it's fast. But beyond just numbers, how can we actually use this technology? You mentioned the paper shows some specific applications.
Yes, and this is where the explicit nature of the Gaussians really shines. It allows for things that are hard or impossible with implicit models.
Like what?
Like semantics-aware compression from machine vision. Figure 10 illustrates this beautifully. Think about AI models getting bigger, needing efficient data transfer. We don't just want small files. We want files that preserve the information the AI needs.
Right, preserve the important stuff.
Exactly. Because ImageGS uses explicit Gaussians, you can guide where they get placed using things like visual saliency maps. Equation 8 shows how they did this. Use a standard saliency predictor and bias the Gaussian initialization probability towards salient regions, using a low lambda like Mato-11 to balance.
So more Gaussians cover the important objects or areas.
Precisely. More representational power goes to the semantically critical parts. They tested this with a visual question answering task using Bilipy. At a very low 0.2 BPP, the ImageGS compressed image, guided by saliency, allowed the VQA model to get the right answer much more often than a JPEG compressed image at the same bitrate.
How much more often?
In their test set of 20 questions, ImageGS matched the reference answer 12 times, while JPEG only matched 4 times. A huge difference. It shows ImageGS can preserve task-relevant features way better under heavy compression. Massive implications for edge AI and efficient data transfer.
Definitely. What was the other application?
Joint image compression and restoration. This leverages the inherent low-pass nature of Gaussian functions. Figures 11 and 17 show this. ImageGS acts as a sort of natural denoiser and artifact remover during compression, especially at low bitrates.
How does that work?
The limited budget of Gaussians forces the model to prioritize representing the main image structures. It doesn't have enough capacity to perfectly replicate high-frequency noise, like sensor noise, or artifacts like JPEG ringing or banding. So it implicitly smooths them out while preserving the important content.
So compression is restoration in this case?
Effectively, yes. They quantified it. On noisy photos, they got average gains of about 1.8 dB PSNR and 0.011 MEMS SIM compared to the noisy input. On JPEG artifacted images, gains were smaller but still positive. And the key is this happens automatically. No separate denoising step needed. It just emerges from the representation itself.
That's really elegant. Okay, this has been an impressive deep dive, highlighting a technique with clear advantages and fascinating applications. But like you said, every innovation points to new frontiers and challenges, doesn't it? Where do the authors see this going next? What are the limitations?
Indeed, they're quite upfront about both. There are two main areas they highlight for future work, stemming from current limitations.
Okay, the first one.
Spatially adaptive optimization. While it's content adaptive now, the current system tends to prioritize larger features. It can sometimes struggle, especially on natural images, with preserving really fine pixel-level details perfectly. That Gaussian smoothing can slightly blur the absolute tiniest textures.
Which relates back to the performance dip on CLIC 2020.
Exactly. So the plan is to explore using things like dynamic binary space partitioning trees. Think of hierarchical grids that adapt to the image structure. These could help guide Gaussian placement more effectively at multiple scales.
A more hierarchical approach.
Yes, and also adaptively scaling the gradients during optimization, so that small features get treated with comparable importance to large ones. The goal is to better capture that full spectrum of detail, from broad strokes to tiny textures.
Makes sense. And the second limitation or future direction?
Extending to dynamic content. Right now, ImageGS is purely for static images. But the success of Gaussians splatting in 3D for dynamic scenes offers a very clear path forward.
Applying it to video.
Essentially, yes. The idea is to model the motion of the 2D Gaussians over time, tracking how their position, shape, color evolves frame to frame. This could lead to incredibly efficient video representations.
Applications there.
Huge potential for things like panoramic video streaming in VRR, where you need compact, high-fidelity video that can be decoded and rendered extremely quickly. Imagine streaming complex animations or live-action video as just evolving sets of Gaussians.
That would be quite something. Okay, so wrapping this up. This deep dive into ImageGS has really shown a powerful new way to handle images. So, what does this all mean for you, the listener? Whether you're deep in graphics research, developing AI, or just following the tech, it means we're seeing a fundamental shift, potentially, in how we represent and interact with visual data, especially for real-time needs. ImageGS really stands out. It's content adaptive, uses these neat 2D Gaussians, gets great rate distortion, it's hardware-friendly for random access, gives you flexible quality control via that LOD stack, and it really seems to capture non-uniform features well, even at low bitrates. It feels like a significant step.
I agree. And to me, what ImageGS really highlights is the power, the elegance, and maybe the underestimated potential of explicit representations in graphics and ML. Instead of a purely implicit black box, you have these tangible primitives, the Gaussians, with clear physical meaning.
Right, interpretable components.
Yes. And when you combine those intuitive primitives with a fully differentiable rendering pipeline, you unlock this amazing synergy. You get systems that are efficient, adaptable, high fidelity, often outperforming methods that are less flexible or less interpretable.
A compelling combination.
It really is. And maybe a final thought to leave you with can be how these explicit content adaptive representations might fundamentally change the game for edge computing, for on-device AI, places where every kilobyte, every computation cycle is absolutely critical. ImageGS and ideas like it could really push the boundaries of what's possible for visually rich applications running right there on your phone, your headset, your car, anywhere with tight constraints. It's not just about better compression. It's about enabling new kinds of visual experiences.